Another little comic to get your evening of math started. Tonight's lesson is going to be on solving equations with variables on both sides of the equal sign. Our object of the game has stayed the same. We need to get the variables on one side and the numbers on the other. We need to solve or isolate our variable. Remember that variables can only be combined if they are on the same side of the equal sign. We cannot combine across the equal sign. The equal sign forms the Great Wall of China. You cannot go through it, you must go around it. So we will add or subtract to move the variables to one side. And remember, what we do to one side, we must do to the other. So let's see what this looks like in practice. Example 1, I'm going to draw my Great Wall of China here to keep myself organized. And I'm looking at this and I have a 7x on one side and a 5x on the other. I need my x's all on one side. So I like to keep my coefficients positive. So I try to strategize and figure out which side to move them to. I'm going to move the 5x to the left by subtracting 5x from both sides. When I do that, I get 2x on the left. These cancel into 0 by the additive inverse property, and then by the additive identity, I'm just left with 8. Now I just divide both sides by 2, and my final answer is x equals 4. Now this is where I can really tell if you're getting creative with your checks. Watch what happens when I take 7x equals 5x plus 8. In this case, you can't just make up the answer and know that it has to equal something because I have a variable term on both sides. So I will be able to tell immediately if you didn't do this correctly. I get 28 equals 20 plus 8. Yes, that is true. Number 2. Again, I'm going to draw my Great Wall of China here, and it looks like it would be a good idea to move my 3w to the left because then I'll keep my coefficient positive. I get 2w plus 3 equals, again, by additive inverse and additive identity, I get -5. Then I'm going to subtract 3, and so I get 2w by additive inverse and additive identity equals -8, and w equals -4. I can check that by plugging into my original equation, and in that case, I'm going to get 5 times -4 plus 3. Does that equal 3 times -4? Minus 5. -20 plus 3, does that equal -12 minus 5? Yes, -17 equals -17. Now let's take a look at 3 because the check is kind of interesting on this one. Don't get tricked here. What do you want to do? Where do you want to collect your x's? I think it's a good idea to add 5x to both sides because if I do that, my coefficient stays positive. But a lot of students get confused by this and they think that the x drops out. I'm not combining across my equal sign here. I'm not combining the -5x with the 5x. I'm moving it by using inverse operations. I get 10x plus 8 equals 7, so I'm going to subtract 8 from both sides, which gives me 10x equals -1, and x equals -1/10. Now you're not going to be happy with that, but I told you needed fractions, and I wasn't lying. 5x plus 8 equals 7 minus 5x. Plug in the -1/10, so that's going to give me -5/10 plus 8. Does that equal 7 minus -5/10? That's going to be -1/2 plus 8. Does that equal 7 plus 1/2? Sure. 7.5 equals 7.5. So you could probably work on the rest of these and come back and check your answers. Quite a lot of work here to represent these numbers 4 through 7. Notice that I didn't wimp out on my checks. I did the checks even if they were fractions, like number 5. It actually works out not so bad. Be careful when you're doing checks not to get over involved with the details. In other words, I didn't worry about making that a mixed number. My objective here is to get the left side of the equation equal to the right side of the equation. And improper fractions are fine. That worked absolutely beautifully for me. Okay, so 4, 5, 6, and then 7 also was a fraction, and that one worked out perfectly. Hopefully you are understanding this. If you are not, please jot down some questions and problems specifically that you had, and we can address them tomorrow. Have a great night, everybody.